Alright, so section 4.9 talks about Newton's method. Newton's method is an example of iteration. So let's talk about this. So what Newton's method does is it allows us to approximate roots when f of x equals 0. It also helps us to find what we would call the zeros of an equation. So we know for linear equations f of x equals ax plus b, our root is found by x equals negative b over a. And for quadratic equations, we use the quadratic formula. There are also formulas for degree 3 and 4 polynomials. They're really long. You can find them online, or I think it might be in the back of our textbook. But the thing is, for degree 5 and higher polynomials, these nice equations don't exist. Similar difficulties exist for finding roots of non-polynomial functions, such as trig functions and things like that. So what we have is Newton's method, which allows us to approximate roots. To estimate the roots, what we choose is an x sub 0 close to the root, and we find the tangent line at x sub 0 f of x equals 0. Now, that's going to give us where the tangent line intersects the x-axis, which we call x sub 1. We then continue the process again and find the tangent line at x sub 1, f sub 1, x sub 1, where this line intersects the x-axis and is now x sub 2. And we keep doing this over and over and over again, and we call this an iterative process. It repeats. The formula for this process is x sub n equals x sub n minus 1 minus f of x over f prime of x. So let's work through an example. So I want to find the root of a polynomial, x cubed minus 3x plus 1. I never said this didn't work for cubics. It's just typically for cubics we have nice formulas. Over the interval 1, 2, and let's let x sub 0 be 2. So first thing I need to find is f prime of x, so I got to take the derivative, and that's going to give me 3x squared minus 3. So x sub 1 is going to equal x naught, because of our formula, x naught minus f of x naught over f prime of x naught. X naught is 2. If I plug 2 into my original formula, f of x, I will get 3. If I plug 2 into my derivative, I get 9. And that gives me 1.6 repeating. And I'm writing this as a decimal for a reason, as you will see as we move on. So if I have x2, that's me x sub 1 minus f of x minus sub 1 over f prime of x sub 1. That gives me 1.6 repeating minus f of 1.6 repeating divided by f prime of 1.6 repeating. And then I get another number. I get 1.5486. If I complete this process again and again, I get 1.53239. X sub 4 gives us 1.53201. X sub 5 gives me 1.532. So we can kind of see that the root this is approaching is this number right here. It's going to keep getting really, really close to that number. And we can do that as many times as you want. And you can round as many decimals as you want. In the homework, it should give you instructions for how many decimals to round to. Let's work through another example, except now I have the same polynomial, but I'm going to look over the interval 0, 1, and let's let x equal 0. So I want to calculate x1 and x2. So first thing I do is I take my derivative, which we knew to be 3x squared minus 3. If I let x sub 0 equals 0, x sub 1 equals 0 minus f of 0 over f prime of 0. So I get 0 minus 1 over negative 3. Well, two negatives make a positive, so I have positive 1/3. Now x sub 2 is going to be 1/3 minus f of 1/3 over f prime of 1/3. That equals 1/3 minus negative 1 over negative 2.5. So I have 1/3 plus 2/7, that's the same thing as this is a fraction, which equals 7/21 plus 6/21, which equals 13/21. And we could keep going if we wanted to get closer and closer to finding the true root of our polynomial. Remember, it's an iterative process, which means I could go on forever and ever and ever and keep going. So when at x sub n the derivative of f prime of x is 0, but at f of x sub n doesn't equal, because of this, the tangent line has a slope of 0, and thus the line will not intersect the x-axis, and this would mean we'd have to stop our iterative process. So these are some examples of failures of Newton's method. Another failure would be finding the wrong root, okay? Make sure you have a tiny little interval. X sub 0, x sub 1, x sub 2 may approach a different root than the desired root. So I'd always recommend going into Desmos or your graphing calculator and graphing your function. It's possible that our approximation does not find the root we're looking for, but finds another root. This often occurs when we don't choose an x close enough to our desired root. If we had chosen an x, say if we had let our x not be right here, then the tangent line at this point would have, found our root really closely. So be careful to choose a point close enough to your root. Another one is when approximations fail to approach a root. So let's work through this example. So f prime of x equals 3x squared minus 2. x1 equals x sub 0 minus f of x sub 0 over f prime of x sub 0. That gives me 0 minus 2 over negative 2, which is going to give me positive 1. Cool. So now I have x sub 2 equals 1 minus 1 over 1, which is 0. And if I plug in x sub 3, I get 0 minus f prime of 0 over f prime of 0, which would be 0 minus 2 over negative 2, which is again a positive 1. So this is going to keep repeating and switching between 1 and 0 the entire time. Okay, so that would be an example of us failing to approach a root using Newton's method.